Hello. In the previous two videos, we were discussing Kummer theory. In the first one, we proved the cyclic case of Kummer theory. In the second one, we stated the Kummer theory for finite abelian extensions. We proved the maps that are involved in this statement are well defined, and we showed certain properties of the dual groups in order to make sense of the statement better. And we also proved that the Kummer pairing is a perfect pairing. Let me go through these statements again. So what is the Kummer theory for finite abelian groups? Kummer theory says that in the setting that if f is characteristic 0 and it has enough roots of unity, meaning I assume that it has an element of order n, we fix an algebraic closure f bar of this field. Then there is a bijection between finite abelian Galva extensions that have exponent n and subgroups, finite subgroups of f cross over f cross to the n. You see, here it's much more subtle than the Galva correspondence. In Galva correspondence, we are only working with the automorphisms of f bar over f, which is not an, so to speak, internal property of f. We have to go outside. We have to understand f bar in order to understand this bijection. Here, we are working within f bar. We are looking at subgroups of f cross over f cross to the n, and we are getting this kind of bijection internally and externally. All extensions of f with certain properties, all subgroups of f cross allowed by f cross to the n with certain properties. So this type of phenomena that we want to understand extensions of f internally had been extended massively, at least for Q. And there is this general program that's called Langland's program. Its goal is to understand this kind of bijections. But at the moment, we don't know much about it. In certain cases, we have some understanding, but the full generality of Langland's program is far from the finish line. But nevertheless, one of the starting points would be understanding those finite quotients of the full automorphisms of f bar over f that are cyclic or that are abelian. Under certain assumptions, it would be Kummer theory. With no assumptions over Q, if I just want to understand abelian quotients, this is studied under the class field theory. It's called class field theory. So there is a vast theory on this. But in this course, we focus only on the easy case where we have enough roots of unity in the base field, and we can use Kummer extensions to study these type of extensions. So the goal is to show that we can define this lambda and delta starting from an abelian group, starting with a finite subgroup of f cross over f cross to the n. We take coset representatives and add the nth roots of those coset representatives to the base field. That would be our lambda of the subgroup, and delta of an intermediate subfield with abelian Galva extension of exponent n would be similar to the cyclic case E cross to the n intersection with f cross over f cross to the n. We proved that both of these maps are well defined, and we wanted to show that they are inverse of each other, and moreover, we wanted to show that the Galva group of E over F is isomorphic to the dual of delta of E, if E over F is an abelian extension of exponent n. Now, what is the dual of an abelian group? That's what we discussed, and we defined it to be the set of all the group homomorphisms from A to the unit circle. We showed that we can, by pointwise multiplication, we can make it into a group. And we proved that this group is in fact, this group has the same cardinality. Did we show it over here? We proved it over here. Yes, we proved that this every finite abelian group has the same cardinality as its dual, and moreover, the natural map that sends, so there is a natural isomorphism between a finite abelian group and the dual of its dual. And what is this natural map? It sends an element A to the function. Okay, so now I need to give you a character of the dual of A. This means I feed it a group homomorphism on A, I give it an element A, and I just evaluate chi at A. We show that this is indeed an isomorphism between A and the dual of A. So this was what we proved about the dual groups. Then we went towards proving the Kummer theory, and in order to show that, we proved that the Kummer pairing is a perfect pairing. So these were parts of showing why it is well defined. But then after that, we got to showing that, okay, it's over here, that Kummer pairing is a perfect pairing. What does that mean? So Kummer pairing is a function from the Cartesian product of the Galva group of E over F times delta of E to nth roots of unity. We showed that that's the meaning of pairing, that if I fix the first component, I get a group homomorphism from the second component to nth roots of unity. If I fix the second component, I get a group homomorphism from the Galva group to roots of unity, which means that fixing the second component gives me an element in the dual of the Galva group. Similarly, fixing an element in the Galva group gives me an element inside the dual of delta V. Now, what we proved in the previous lecture was that if I fix the second component and get an element inside the dual of the Galva group, then this is an isomorphism. So delta of E is isomorphic to the dual of the Galva group. We are interested in showing the other way around, right? So we want to show that the Galva group is isomorphic to the dual of delta V. The question is, can we do it in general? So if I give you a pairing of two finite abelian groups, and I tell you that it's a perfect pairing, that means if I fix the second component, I get an isomorphism from the second components to the dual of the first component, then can I show the other way around? Can I show that if I fix the first component, then I get, so do I get a map from the first component to the dual of the second component, which is an isomorphism? So that's what we want to show next. We want to show that if I start with a perfect pairing, then we can go the other way around. So let's write it down. So we are in the setting. A is this abelian group, the Galva group of E over F. B is delta of E. And we have this Kummer pairing from A cross B to S1, essentially to the nth roots of unity, but in general, we can put it inside S1. And we are told that it's a perfect pairing. That means that F hat from B to A hat is an isomorphism. This is what we have proved for Kummer pairing. That's our assumption. Now I want to say the symmetry between the components, meaning if I want to say that if I fix the first component and then get something in the dual of the second group, I'm getting again an isomorphism. So F tilde of A applied to B is the pairing of A and B. It's the same, remember this is the same as F hat of B applied to A. So this is the same as F hat of B applied to A. So knowing that F hat is an isomorphism, we want to show that F tilde is also an isomorphism. Notice that similar to how we showed f hat is a group homomorphism, we can show that f tilde is a group homomorphism. That part is completely symmetric. So the whole issue is to show that f tilde is injective and surjective. Let's start with injectivity. So as always, it should be easier to show injectivity. Okay, let's see how we can show f tilde is injective. F tilde is a group homomorphism. To show it is injective, it is enough to show that its kernel is trivial. So suppose A is in the kernel. That means what? That means for every B inside the group capital B, f tilde of A applied to B is the constant 1. That means f of A comma B is 1 no matter what B I pick. Remember, this is f hat of B applied to A. So this equality is equivalent to say that A belongs to the kernel of f hat of B for every B in the group capital B. But remember, f hat is an isomorphism from B to the dual of the group A. Therefore, image of f hat is the entire A hat. So this means that when I tell you A belongs to the kernel of f hat of B for every B, I'm telling you that A belongs to kernel of everything in the dual of A. So every chi that I give you in the dual of A is in the image of f hat. Knowing that A belongs to the kernel of everything inside the image of f hat implies that chi of A is 1 no matter what chi I pick from A hat. That means what? No matter what chi I pick, when I evaluate it at A, I get 1. Evaluation at A is given by this L. Remember, we had this L from A to the dual of the dual, that when I feed it a character chi, I just evaluate it at A. I am telling you that no matter what chi I give it, I give you, when you evaluate it at A, you end up getting 1. So evaluation at A is independent of the character that I feed it. It's always 1. So it's a constant function on the dual of A. So that means A belongs to the kernel of L, but L is an isomorphism. So that means that A is trivial. Of course, here I could have also used the lemma that we had earlier to show this, meaning we have proved that for every non-trivial element A, I can find some character that sends A to not 1. Knowing that it is sent A to 1, no matter what character, I can deduce that A is 1. So there are different ways of showing this, but nevertheless, the gist are the same. We deduce that f tilde is injective. Now, how can I show it is surjective? This is injective. As usual, surjectivity is a bit more tricky, but nevertheless, now we have all the needed tools. We can use pigeonhole principle to deduce surjectivity out of injectivity. If I show that these two finite sets have the same cardinality, knowing that f tilde is injective implies that it is also surjective. But how do I know that they have the same cardinality? What do I know about A and B? I know that f hat from B to A hat is an isomorphism. That means B has the same cardinality as A hat. B has the same cardinality as its dual. A has the same cardinality as its dual. So A has the same cardinality as the dual of B. And f tilde is injective from A to dual of B. Therefore, f tilde is a bijection. F tilde is a bijection, and it's a group homomorphism. So f tilde is an isomorphism. So that's exactly what we wanted to show. This is one of the key properties of perfect pairings. So perfect pairing is quite symmetric in terms of the components. If I define perfect pairing in terms of saying that's a pairing that induces isomorphism from the first components to the dual of the second component, it's equivalent to saying that it also induces an isomorphism from the second component to the dual of the first component. Okay, now that we have proved these properties of the perfect pairings, and we showed that Kummer pairing is also a perfect pairing, we are all prepared to prove the Kummer's result for finite abelian extensions. So you want to show that lambda O delta is identity. What does that mean? So I start with delta of E. I assume the delta of E is this finite group. It has these elements. Then by definition, lambda of delta of E is the field that's generated by the nth roots of A1, nth root of A2, and so on. And what we want to show is that lambda delta of E is E. So we need to show this equality. So showing lambda delta is identity is equivalent to saying that if delta of E is this group, then E is this field. So this is what we want. This is the implication that we want to show. We want to show that these two are equal. Again, two sets. When we want to show that two sets are equal, we need to show one is a subset of the other one and vice versa. Let's start with an easy side. When I tell you that delta of E is this group, that means that all these guys belong to delta of E. And what does that mean? It means that I can find some element inside E so that this coset is nothing but alpha I raised to power n, the coset that's represented by alpha sub I raised to power n. And this equality means A sub I is alpha sub I raised to power n times some element of f cross to the n. That means for some c sub I inside f cross, it is c sub I raised to power n. Now I can take nth roots from both sides. So I know that the solutions of x to the n minus a sub I are of the form some power of zeta times nth root of a sub I. So knowing that both these are zeros of the same thing, we can deduce that the nth root of a sub I is some power of zeta times c sub I times alpha sub I. Notice that this is inside F. That means the nth root of a sub I is automatically inside E because, again, alpha sub I is inside E, this is inside F, so this product is inside E. So that means that this side is definitely a subset of E. So F joined with nth root of a sub i's is definitely a subfield of E. Now, we want to show equality. So this is an intermediate subfield of E over F, and I want to show that it is exactly the top one. A good technique is using Galva's fundamental theorem of Galva theory. What is that? There is a bijection between intermediate subfields and subgroups of automorphisms of E over F, the Galva group of E over F. And what is the bijection? Given an intermediate subfield, we look at, given an intermediate subfield, let's say L, we look at the L automorphisms of E. If this L automorphisms of E is trivial, then my field is the entire field. So this means our goal is equivalent to saying that the only automorphism of E that fixes the field F joined with nth roots of A sub I is the identity. So you pick an element inside this Galva group. We want to show sigma is identity. If we show sigma is identity, then we get the claim. We get that E is equal to this, and we are done. Okay, what does it mean that sigma fixes this one? Sigma restricted to this is identity. What does that mean? That means sigma When I apply it to the nth root of a sub I, it does not change it. That means f of sigma, comma, a sub I bar is 1. I mean, remember, this is exactly this fraction. This one divided by this one gives me this Kummer pairing. Knowing that sigma fixes these, we deduce that the Kummer pairing with the second component a sub I bar is 1. Now, a sub I bar is this coset. Notice that these a sub I bars exhaust all A. I mean, exhaust all delta of E. These are all the elements. This means what? This means f tilde of sigma for every a sub I bar is 1. A sub I bar is every element inside delta of E. This means f tilde of sigma is the trivial element inside the dual of delta of E. So f tilde of sigma is the trivial element inside this, but f tilde of sigma from the Galva group to the dual of delta of E is an isomorphism. This is what we proved in the previous step. This is an isomorphism, and sigma belongs to the kernel of f sigma. That implies sigma is identity, and therefore the only element of this group is identity, which means this is the trivial group. That means this field is the entire E, and that's exactly the implication we were looking for. So this shows that lambda O delta is identity. Now let's try to show that delta O lambda is identity. What does that mean? That means what? That means that if I start with this finite group A, this is a finite subgroup of f cross over f cross to the n, then lambda of A, if I denote it by E, what is lambda of A? It is the field after joining the nth roots of the coset representatives to the base field F. When I add these nth roots of coset representatives to the base field, let's call this guy E, then we will have to show that delta of E is the group that we started with. So again, we want to show this equality, A equals to delta of E. We want to show these two sets are equal. That means we need to show each one contains the other one. One side is rather easy. Let's start with the easy side. By definition of delta of E, we are looking for those elements of E that we can raise to power n and end up being inside F. Obviously, when I start with the nth root of a sub I, as I raise it to power n, I am inside F. I get a sub I, and I am inside F. So these elements are inside this intersection, and therefore the coset represented by those are inside delta of E. The coset represented by these guys are a sub I f cross to power n. That means I'm getting the entire group A as a subgroup of delta of E. So this inclusion is rather easy. Now I want to show the other way around. And the key point is the following, that if you want to show equality of a subgroup of an abelian group by the larger abelian group, you can do it using the concept of dual groups. You look at the quotient. These are abelian groups, so every subgroup is a normal subgroup. You look at the quotient. You want to show that the quotient is trivial. If the quotient is not trivial, the dual of the quotient is not trivial, because we proved that every abelian group has the same cardinality as the dual of that group. So that means I can find a character of delta of E over A, which is not trivial. But I can precompose it with the quotient map and get a group homomorphism from delta of E to S1 that has A in its kernel, but it is not trivial. So let's put them together and let's see. Let's go one step at a time. Let's assume to the contrary that A is a proper subgroup of delta of E. Let's look at the quotient. It's a non-trivial abelian group. Let's look at its dual. Because it's the cardinality of the dual group is the same as the cardinality of the group, this would be a non-trivial group. Let's pick a non-trivial group homomorphism. Let's call it chi bar. This is a character of delta of E over A. I can look at the and we can pre-compose it with a quotient map, which means what? Which means I can define chi from delta of E to S1 like this. I start with an element X inside this. I first pass to a quotient by A and then apply chi hat. So it's chi hat of the coset of X in the quotient of delta of E by A. It's composition of two group homomorphisms, the quotient and chi bar. Therefore, it is a group homomorphism. Because chi bar is non-trivial, chi is non-trivial. So we get a non-trivial character of delta of E. Moreover, if I start with A, then first I go to the quotient, I got identity, and then I apply chi bar. So I will still get identity. So A is in the kernel of chi. So altogether, we end up getting a non-trivial character of delta of E that has A in its kernel. Now, what can I do with it? I want to reach to a contradiction, of course. But how? We notice that F tilde from the Galva group of E over F to the dual of E is an isomorphism. Now we are getting an element inside the dual. Because this is an isomorphism, I should be able to find some element of the Galva group that is sent to this character chi. But what does sigma do now? What does it mean that it belongs to the character? F tilde of sigma is chi. F tilde of sigma is chi. That means what? That means F tilde of sigma of AI, for instance, or A bar, let's say, and then I restrict it to AI later. A bar for every A bar is F of sigma of A bar. Now, because this is chi, this is also the same as chi of A bar. In particular, if A bar is in the kernel, I deduce that A bar is in the kernel of F tilde of sigma. What do I know about kernel of chi? I know that A is inside the kernel of chi, and A consists of these elements. So this means that all these, maybe it's better to write it like this. Okay. So this means that all these Kummer pairings of sigma and A sub I bars are 1, no matter what I pick. And remember, this quantity is nothing but ratio of sigma of the nth root of A sub I by nth root of A sub I. Knowing that this fraction is 1, I deduce that these guys are fixed under sigma. But remember, E is generated by F and these guys. And sigma is fixing all of these generators and fixing the base, its identity, when I restrict it to the base. So altogether, we get that sigma is identity. That gives, when sigma is identity, F tilde of sigma is identity, and that gives me a contradiction because I assume that chi is not the trivial character. That gives me a contradiction, which shows that delta or lambda is also identity. We have already proved that the Galva group is isomorphic to the dual of E. That completes the proof of Kummer's theory, the finite abelian case of Kummer theory. Let me finish this lecture by a single example to illustrate how strong Kummer's theorem is. So immediately out of the result that we proved, we can deduce the following, that if P1, P2, Pn are distinct primes, then Q joined with radical of P1, radical of P2, radical of Pn over Q is Galva, and the Galva group of this extension is isomorphic with Z mod 2Z plus Z mod 2Z plus Z mod 2Z n times. So let's see how we can get such a result. We know that Q contains plus minus 1. So it does have enough two roots of unity. Therefore, I can use Kummer's theory and deduce that this Galva group, so when I add the nth roots of unity, nth roots of elements, they are automatically Galva extensions. And moreover, this Galva group is isomorphic to the dual of the group generated by, so then I look at the cosets that are represented by p sub I squared. So I get p sub I, square root of p sub is squared, so that would be p sub 1, q cross squared, p sub 2, q cross squared, and p sub n, q cross squared. Because p sub i's are prime numbers, distinct prime numbers, one can show that this guy is, so this isomorphic to the dual of this one. And because we have proved that, because p sub i's are distinct primes, one can easily show that this is isomorphic to Z mod 2Z plus Z mod 2Z plus Z mod 2Z. I leave it as an exercise for you. And then we have to work with the dual of this one, which means that we are asking what are the group homomorphisms from this two torsion group to circle. But it's two torsion, therefore we are assigning just plus minus 1. Then you can show that it is in fact isomorphic to the group itself. So I leave this part as an exercise as well. So in particular, you get that this is a Galva extension and the degree of the extension is 2 to the n. Using this, you can get a lot of information about this. You can list all the possible intermediate subfields. You can give me a primitive element of this field extension. So I leave all these questions as exercises for you to explore applications of Kummer theory in this easy example. For now.